And without further ado, I would like to introduce Dr. Kurt Gurley, who is the Associate Director and Co-PI of Education at the University of Florida's Powell Family Structures and Material Laboratory. His primary areas of research are wind effects on residential structures and stochastic modeling of extreme winds and structural resistance. He couples field data with post-storm residential damage assessments, lab evaluations of component capacities, and wind tunnel studies to model the vulnerability of residential structures to hurricane wind damage. He received his BS in Aeronautical and Astronautical Engineering from the University of Illinois, and his MS and PhD in Civil Engineering from the University of Notre Dame. In 2007, Dr. Gurley received the IAWE Junior Award for Outstanding Achievement and has successfully written many NSF grants to further research in his discipline area. Please join me in welcoming Dr. Kurt Gurley to this month's NHERI Graduate Student Council meeting.
Hello, everybody. Do a quick mic check. Does this thing sound okay? All right. Every once in a while, my microphone arbitrarily makes me start sounding like Darth Vader, and I don't know why. So if that happens, just let me know, because all I have to do is unplug it and plug it back in and it fixes itself. But I don't know that it's happening. Only the people on the receiving end do. So feel free. I am going to get into PowerPoint mode here in a moment, but before I do, I intend to make this presentation slightly interactive, meaning you guys are welcome to kind of shout out answers or feedback, whether you're more comfortable typing something into the chat if you want to offer your opinion, or just unmuting and yelling something out. I don't have a objection to either one of those, and I'll cue you for, when it's time to give me your thoughts. And it occurs to me after that very nice suspiciously terse introduction, but I'll take it, that it'd be a good thing for you guys to pay attention, as the way I've structured this presentation would be very similar to how I would structure creating an NSF grant. That is a proposal to get money. That is to say, the most important thing about this is the story and the narrative of not only what am I doing in the technical stuff, but what problem am I trying to solve, and why might it be important? Right. So when you are the person writing the grant to NSF, the most important people to convince are, of course, the panel of experts going to be reviewing your proposal and giving feedback to the project manager. Usually the most important people on that panel are the non-domain experts in your field. So when I write a proposal to NSF, most of the people reviewing my proposal know a good deal about wind engineering and hazard engineering, and some of them don't. If I can get those people on my side right away with a very clear statement on the front page, this is the problem, this is why it's important. I'll give you all the technical stuff in the rest of the document, but I want you on my team from the get-go. So think of how I'm structuring not just the order of the pictures, but the intent here is for you guys to all understand exactly what I'm doing and why I'm doing it, whether you know anything about wind or not. If you can do that in your proposals, then you're going to be a winner. Okay. Let me jump into, I'll share the screen in a moment. I got to get myself set up here. So let me step through. I'm just zooming in so I can see more faces on this screen. All right. So this is a joint, the original title I gave was something about, the basics and the new and wind tunnel modeling. And it really is what this is about, and I'll explain that, but I didn't actually copy and paste that title. So what I'm actually going to step you through is a project that I have currently going on with a faculty member at Johns Hopkins. And something to know, again, when you're thinking about your future, Mike Shields, my partner at Johns Hopkins, is not a wind engineer. He's more of a machine learning, stochastic modeling person, but he's collaborating with someone who does experimental work. So your opportunities are as broad as your willingness to ask people what they're interested in and how you can help, right? So with that, let's go ahead and, but here's the subject of today. This is a rigid model of a residential structure. It's a 1/50th scale. So it's, it's about 13 centimeters tall or so. And it's actually a model of a real home that's in the panhandle of Florida. you can see on the in the background setting, it's sitting in our wind tunnel. You'll see a lot more pictures of the wind tunnel. And the picture on the right is an example of what we might do from the data we would collect from this model after an experiment, right? The color contours represent the amount of uplift force acting on the surface of that model. And of course, this model is sitting on a turntable, so we can change the direction of the wind, because what the model feels has a lot to do with not only its shape, but the direction the wind is coming. In addition to a third important component, which is what this project is about, which is the nature of the turbulence as it's approaching the model, right? So very humble beginning. We just have a rigid model, and we're going to take pressure measurements on the surface of that model and then see where that takes us. This is kind of important to set the table because, actually I should go backwards one again. This is the kind of experimental work that is done to inform, for example, ASCE 7 wind load provisions. If you've come across those before, and you might if you haven't, you know, the prescriptive measures that say, you will assign this many pounds per square foot to the roof of your building when you're designing against wind loads. The numbers you get out of the code come from experiments like this, although they were done on much less complicated geometries, just simple rectangle buildings with gable roofs and so on. So what we're trying to fundamentally explore here is something that could directly feed into what we do to make building codes, which means it could eventually change how structures are built in the long run. Or conversely, just as good, verify that what we're doing now is just fine, right? That's an important thing. I'm going to give you some hypotheses in a minute, but we don't care if the hypotheses wind up panning out or not. It's still going to be something interesting no matter which direction it goes. So if you turn over that same model, you see it's got all these little tubes connected to it. And some of you know about bluff body and wind loading, and some of you don't. So I'm speaking to those who haven't seen this before. And there's 512 different taps all coming down to these metal connectors, and all those metal connectors connect into the device on the far right, which is a scanning valve system is connected to a series of pressure transducers, which cycle through. So while we're actually running an experiment, each one of those little holes on the roof of my model are sampling the instantaneous pressure that it's feeling right at that spot, at 512 different spots on the model. And that's where those color contours come from, for example. All right. So the motivation here is we want to determine the influence of higher order characteristics of the approach turbulence on the peak wind loads. And so here's your first opportunity to give me some feedback or your opinions. And if you really know what the answer is, maybe give someone else a chance who's guessing. But a traditional boundary layer wind tunnel experiment, which is what is the backbone of what we're doing, typically starts by dictating what the first order and the second order characteristics are of the approach wind field. And what I mean by first order is just the mean wind speed, and then the coefficient of variation, standard deviation divided by the mean, coefficient of variation. In wind engineering, we want to be special, so we gave that a different name. We call it turbulence intensity. Turbulence intensity is just coefficient of variation of the fluctuating wind as it's approaching, right? And when I say a profile, I mean the nature of the mean and the variance is going to change as we go up in height. So give some thought to the two question marks on the bottom right. What will happen to the mean wind speed that we measure as we go from the floor and go higher up in the wind tunnel? And then at the same time, what will happen to the coefficient of variation, or the turbulence intensity? How intense will the fluctuations be near the floor as opposed to going higher up? Think about that for a moment. If you want to pop a guess in the chat, feel free. But that's what I want you to kind of be focusing on. Now we're going to control the nature of that turbulence and the mean by controlling these little elements. Can you guys see when I'm moving my cursor on the screen? Okay, so we have all these little elements. We're going to spend more time talking about them, but I want you to give you a physical feel for this to begin with. So imagine yourself sitting and watching a very nice calm stream, and the water is moving from the back of the picture towards us, right? And it's nice and calm. You can see little ripples, but not much is going, and the water is moving. Now very gently place a few boulders in the stream and imagine what's going to happen. You're going to get turbulence because the fluid has to move around the boulders, and that generates what's called mechanical turbulence, right? Well, the wind tunnel is just throwing rocks in a stream. It's generating mechanical turbulence. And if this movie works, you'll see what I mean. It's a time-lapsed film video of all the rocks in the stream are the little rectangles you see in the floor. And if we make them higher, it's putting big boulders in. If we make it lower, it's putting small boulders. That controls how much turbulence we're generating, right? And then that device that's hanging vertically in the front is an automated gantry system. You might be able to see right here on the front. These are 3 little things that look just like dental drills. And those are measuring very precisely what the wind speed is at the spot where the tip of that probe is. But we need to measure the wind speed at lots of different places. So the probes are going to be fixed for 30 seconds, take measurements, then they move a couple of millimeters, then they move, then they move, then they move over. So that's what this time lapse is going to be showing. Hopefully you guys will see something other than weird. Can you see it? Is it kind of smooth or not? Okay, good. So the wind is coming from the back. You can see the elements, the rocks in the stream changing as we go from one experiment to the next. And you can see it does 3 vertical strokes before we move to the next experiment. In reality, every one of these series of experiments takes about 20 minutes as opposed to a few seconds that we're looking at. And this high level of automation that you see, our ability to push a button and change all the rocks in the stream, is a big enabler for what we're trying to discover. Oh, there's Ryan, our technician. They always has to get in the picture. What we're trying to discover is enabled a lot by our ability to do this rapidly. This is how most wind tunnels operate already. They put rocks in the stream, but they get on their hands and knees and move the blocks around by themselves, right? So if we can go from one to the next in less than 90 seconds instead of a few days, that's a huge upturn in scientific in discovery output potential. Okay, so moving on. There we go. So here's the same figure before. The wind speed. Hopefully you kind of figure this out. The wind speed, the average wind speed, is going to increase as you go higher up because of it's sticking to the floor, so to speak. But the turbulence reduces as you go higher up because the turbulence is most extreme down near where the elements are. And as you get farther and farther up away from those roughness elements, the turbulence decreases. Okay, so here's what we're trying to do. We're moving from just describing the approaching wind field to the nature of the pressure that's now being felt on the surface of the building. So we got our model, and the 2 things we're controlling in the wind tunnel is the turbulence intensity and the mean profile. And we do that by moving the rocks in the stream, as we just showed. And now we have an overhead view of the same model, and all those little plus signs represent a specific spot where we're measuring pressure during the experiment. And let's highlight one, because now I'm going to show you the time history that we measured at that particular spot during one experiment. Before I do that, here's the equation that we're going to use. This is the magic number that all wind people focus on. This is a non-dimensional thing called a pressure coefficient. You can think of it as a filter that translates wind speed into wind pressure. And we just take the P here is what's actually being measured on the surface by that red dot. The P reference is the weight of the atmosphere sitting on top of us all right now. And then the 1/2 rho, V squared rho, is the density of air. V is the reference velocity. That means we pick some height in the wind tunnel and we measure the mean wind speed at that height. That becomes the reference velocity. If we're using ASCE 7 to do a design load, that reference height is usually 10 meters for a frame of reference. All right. Now, that pressure coefficient, once we take the raw pressure and process it through that equation, we now have a time history of pressure. You can see it's negative, which means relative to the atmospheric weight, it's pulling up on the roof as opposed to pushing down on the roof, right? Because of separation happening over the roof. And so we're going to be interested in capturing this negative behavior, the mean value, the fluctuations, and the extremes. So we can process that. We can just take a mean value of that whole time history. We can take an RMS, or standard deviation, of the whole time history. And of course, those answers are going to be a function of the building shape, the wind direction, and the profiles meaning the nature of the approaching turbulence. So this time history would change its nature if I went and rearranged all the rocks in the stream and repeated the same experiment on the same building. All right. So different wind tunnel facilities, we're still drilling down to the motivation. Different wind tunnel facilities testing the same model, and we've done this lots of times, different studies, do a good job of matching the first and second order pressure coefficients if they use the same target profiles. That means if 2 different wind tunnels produce the same first and second order approach flow, when they measure the mean and the second order pressure on the same model, they get pretty much the same answers, which is a good thing. We want consistency. The peak pressures, which I'll illustrate in a second, used for the design, so the stuff that actually shows up in the codes is actually a peak pressure and extreme value analysis, and it's not the things that we just looked at. These peak pressures are also a function of the approach turbulence, the building shape, and the wind direction. When we look at what different wind tunnel facilities measure in terms of peaks, there's a great deal more variability between different facilities trying to duplicate the exact same thing. And so this causes a lot of uncertainty. If we happen to use wind tunnel A to inform the wind load provisions, but wind tunnel B would have gotten a different answer, then that's an unclosed gap, right? So if we start where we were before, here's the same time history. To get a peak pressure coefficient, we would, for example, chop up our time history into a series of smaller chunks. In each one of those chunks, we would identify the single peak value. I'm interested in the negative uplift extreme. That's why I'm circling the bottom values, not the top values. And then we would then choose those as our only data, just the extreme values every so many seconds, and then do an extreme value analysis on that. For example, create an empirical cumulative distribution function. Now all we got to do is pick a threshold that says, I will define a peak pressure coefficient as that which there is only a 10% probability of any random sample exceeding. Follow me? It's not actually 10%. I'm just kind of picking a number. That means on the vertical axis, there's my 10%. I walk over and then down, where that arrow ends on the horizontal, that would be my definition of the peak pressure coefficient for that model at that spot in that wind profile from that wind direction, right? So this peak is also a function of what we initially tell the wind tunnel we want, how we rearrange the rocks in the stream. But we suspect that's not the whole story. And that's what we're trying to explore here. Is that enough? Just defining the mean and the second order profiles, which any wind tunnel can do, is that enough to get a consistent set of peaks? So here's motivation again. Is possible that the peak differences between different facilities that have the same first and second order profiles, they might have different higher order turbulence approaching the model, because no one really measures that because it's a very difficult thing to control. So wind tunnel modeling of higher order turbulence and its effect on structural loads and response is what this research project is about. Higher order just means, if you've taken a statistics class, think, we've talked about mean and standard deviation or coefficient of variation, just go to skewness and kurtosis. Third central moment, fourth central moment. And that's what we're talking about when I say higher moments, nothing too complicated. So again, in a picture, here's what's going on. We've got two different boundary layer wind tunnel facilities. We give them the same model. Both facilities match the first and second order profiles. We don't know if their third and fourth order profiles are the same because they don't even measure them or report them. They're able to match the first and second order pressure coefficients that result on the model, but they get different peak pressure coefficients oftentimes. And so we think this here is the gap that we need to explore, whether that's the missing link as to why we get different peak results from different wind tunnels. So, if I told that story on the first page or first 2 pages of a proposal, you don't need to know anything about wind engineering to know, oh, I get why they're doing this. I see where the gap is. This could be important. Let's read more and pay more attention. All right. So hypothesis, we can identify multiple heterogeneous roughness element terrains. That is to say, we can rearrange the rocks in the stream in lots of different ways and still get the same first and second order profiles, equivalent profiles. But maybe the third and fourth profiles would be different for different arrangements of rocks. And when two different wind tunnel facilities both match the first and second order, they may not be matching the third and fourth orders, and that's why the differences come from. So here's the tools to do the work. First is a little bit closer look at that wind tunnel. This is the device in the middle, those rocks, the elements that go up and down at the push of a button. We call those the terraformer. That's our nickname for it. So we can do lots of experiments very quickly with the terraformer. And then we're also using, this is where the Johns Hopkins folks come in. We're going to be using machine learning to drastically reduce the number of experiments we have to do before we discover interesting things. And so here's the basic concept. Since we have, it turns out, 1,116 individual rocks, each one of those elements, we have, I forget, 62 rows of 18, I think it is. And every one of them can be individually controlled. That means we have more than 1,100 degrees of freedom. So we have to be careful and parameterize our space. What we're going to do is start off by just using simple sine waves to describe the flow over the rock. The shape the rocks are going to make as we move from the fans to the test section is going to look like a sine wave. So we're looking at a side view here of what the terraformer looks like over 62 rows, right? And if it's a sine wave, that means we can parameterize it by the amplitude of that sine wave. And the wave number, another way of saying frequency. right? So we can have very fast moving, very slow moving, high amplitude, low amplitude variations of the sine wave. And that's what we're going to be doing to the terraformer and then measuring the approach turbulence that results from these different shapes. So we're systematically rearranging the rocks in the stream. I won't dwell on this one. I think we don't really need it, and I don't want to run over on time. It's really sort of a detailed look at the sequencing of when we do an experiment, when it gets fed into the machine learning, how the machine learning feeds back into the next experiment, and so on. But let's focus on the basics. So first we have to start with a benchmark. So the benchmark experiment is going to be every one of those elements is going to be set at exactly the same height. It happens to be 8 centimeters. So every one of them is going to be 8 centimeters off the ground. So it's a homogeneous terrain. Every element is the same height. And then we measure the turbulence intensity at the test section. Then we repeat that same experiment many times, because every time you repeat the experiment, there's natural variability, of course, right? So that dashed line would represent the mean second order turbulence intensity profile after repeating the same benchmark experiment 25 separate times to really help define the uncertainty. That's the important thing here. So here's a look at all 25 of our experiments and what the resulting second order profiles look like as a function of height. So obviously we will consider every one of these experiments identical, statistically speaking, because they're repeating the same experiment. So now when we start varying and putting heterogeneous commands into the terraformer and looking at different ways of rearranging the rocks, we can use this collection to say whether that second order profile is equivalent or it's not equivalent in a statistical sense. So here's our 25 benchmarks. We don't need to worry too much about the equations here. It's just a way of saying we're just looking at an L2 norm difference. So when we place I don't know if I have a picture of it, I guess not. If I was to draw now another experiment on top of this one, and maybe it fluctuated away from the group a little bit, we can statistically quantify how much that fluctuation is and whether it's significant and whether we could call that one equivalent or not. That's really what these two equations are talking about. How do we define second order equivalence among different profiles? All right. So methodology wise, we've already done our benchmark. So that benchmark experiment's represented by the star and actually the solid line. So this horizontal and vertical axes are what we call the parameter space. This is the wave number as we change the frequency of the sine wave that makes up the terraformer, and then the amplitude. So the mean amplitude is always 80, but a small amplitude will be 80 plus or minus a little bit, 80 millimeters. A big amplitude will be as much as plus or minus 8 centimeters, 80 millimeters, right? So, and all these blue stars are the results of an initial series of 25 tests that we populated to get started. So we're going to use the outcome of each of these experiments, each of these blue stars, to train the machine learning algorithm. And what I mean by a star is any one star represents an experiment. That means that was the wave number and that was the amplitude that was given to describe the rocks in the stream. And then we had our gantry move our dental drill up and down and measured each location for 30 seconds. And then we get our second order profile. That means I've now completed one experiment. So this represents 25 different experiments, 25 different profile measurements. And then we evaluated the difference between the second order profile that results from these experiments and the benchmark we just talked about, whether they're the same or not. We have a quantification of how different or not they are from the benchmark. Then that differential and the parameter space is what feeds the machine learning. All right, so we feed those results from the initial 25 into the machine learning. I'm not getting into any details about how the machine learning works. You all know the basic idea of machine learning is a pattern recognition system. And so the input is the terraformer shape, the sine wave, and the output is the error between the resulting second order profile and the benchmark. And so the the red dots that showed up in our parameter space are now, for example, experiments that the machine learning told us to do. The blue ones we picked randomly from our space. The red ones say the machine learning is telling us, I'll learn the most about this if you put an experiment there. And then it takes that result, feeds it into the collection of what it's got and says, now I want you to go there, right? And you can see it kind of, this is just cartoonish illustration. I'll show you what the real surface looks like in a few slides, but I want you to get the general sense. So every red dot is now the machine learning telling us, do the next experiment there, there, there. And eventually we want them to figure out where to do the experiments to establish the contour. So we expect that there will be a contour that everywhere inside that contour would be statistically equivalent to our benchmark experiment. We would call it the second order equivalent contour. And then I'll tell you about why that would be important as we get to the end. Here's just one snapshot of the result of one experiment compared to the benchmark. On the left-hand side is our turbulence intensity. The black is the mean of all of the benchmark experiments. The red dashed lines basically represents the fluctuation among our 25 baseline identical experiments. And so we can visualize this particular experiment, the blue one, is kind of lying inside the boundaries for the whole way. So this would be an example of a second order equivalent experiment. Meanwhile, the skewness and the kurtosis profiles you see are a little bit more squirrely, right? So hopefully we'll see cases where second order equivalent is easy to see, but we don't get equivalence. The blue line would vary wildly from the black line. In the higher order, skewness and kurtosis. Skewness is third order, kurtosis is fourth order. That's what I mean by higher order. So here's a little cartoon of a number of different terraformer configurations that have been done, just to give you a sense of the variability. So all these are different sine waves that have already been plugged in and tested and so on. And so we got a second order profile for each one of these. And actually we've done, I showed you like a handful, but we've done over 1,000 different configurations to date. So lots and lots and lots and lots of high throughput that we wouldn't be able to do without the automation in the facility. All right, getting to the semi-conclusion here. Here is a view of the real parameter space and the real second order equivalents that we've discovered so far. This is just, again, describing the terraformer as a sine wave. The wave number, or the frequency, is the horizontal axis. The amplitude, how big is that sine wave, is on the vertical axis. The green area is the second order equivalent contour discovered by the machine learning and the terraformer working with each other. Everything in the yellow is an experiment that was statistically different from the benchmark, meaning that's not the second order equivalent. So now what we know is any experiment that we pick, this wave number, that wave number, this amplitude, any one of these in the green would give us an equivalent second order. In other words, any other wind tunnel facility wouldn't differentiate between them at all. They would both give you the same second order statistics. Now, just as in terms of what we got out of machine learning, this was a result. This contour came from the 25 initial samples, the blue stars, and then the machine learning told us it was done when it did 197 individual experiments, each time reconfiguring the terraformer slightly. And this is our best estimate of how many experiments we would have had to have done without machine learning. If without machine learning, we would have just gridded the parameter space and just started plugging away, right? Sort of brute forcing our way through. We could have gotten the same precision of the second order contour if we had done 2,200 experiments instead of less than 225 experiments. So machine learning in this case saved us an order of magnitude in effort. And every experiment takes us minimally 20 minutes and usually more because there's maintenance cycles and all that kind of thing. So we're talking about real money. It takes electricity to drive the fans and human people that are being paid by the hour and all sorts of things. So machine learning is a big benefit to us here. So the guy at Johns Hopkins and his student who know nothing about wind engineering are driving the boat here, perhaps offering the most important thing. Here's where we're going next. Now, going back to our model, you might have wondered what the heck happened to that model, right? Model's not in anything we've done so far. Now we're going to put this model in the wind tunnel and we're going to pick experiments. We'll pick experiments in the green zone, second order equivalent, and we'll make sure we cover this. We'll do lots of experiments. So imagine any one of the red dots that are inside the green, we're now going to subject this model to, and then measure the peak pressure coefficients. And if our hypothesis holds up, we'll get different peak pressure coefficients, even though all the experiments have the same second order approach turbulence. And just as a reminder of what I mean by peak, it's, you take all these peaks every so often and you collect them and you define a probability of exceedance. So it's premature to say whether our hypothesis is valid, but if it's validated, it can be a significant contribution to wind engineering that will be revealed because, summarizing, building code wind loads are based in part on peaks measured in boundary layer wind tunnels. Peaks are sensitive to higher order turbulence. Higher order turbulence is sensitive to roughness element configuration. Multiple roughness element configurations can be second order equivalent. Therefore, second order turbulence modeling in boundary layer wind tunnels is insufficient to resolve peak loads. Those are not conclusions. Those would be the conclusions if our hypothesis is validated. If it's not, then we discovered that it's a dead end and no one else has to do it, right? So either way, it's a win. Either way, it's going to be a paper that my students and I are going to write. That's the ending official slide. I had a few other slides about other stuff going on at the wind tunnel, but I think to be sensitive to time, I will call that the end and then open up for, I suppose we open up for discussion, Robin, is that the plan?
Holly, I'm going to defer to you because I think we are over time just a little bit. We may move the discussion into the wind research breakout room, but Holly, you get to make that decision.
Why don't we leave it open for 5 more minutes to everyone in case anyone had any questions on that across, and then we can move into the different research groups.
And by the way, write down my name if you do want to talk to me more about it, but you don't want to take up the time. Just send me an email and we'll do our own private little discussion. So feel free.
Thank you for that, Alpha. We appreciate it.
It doesn't seem like
anyone have any questions? I think I saw Jordan's hand. Was it Jordan's hand that was up or Jasmine's?
I was just clapping. It was great. Thank you.
just one comment that was very interesting. Thank you for your great presentation. Thank you.
Thank you. And I know some people on the group, or at least one person, maybe it's you, Simon. I'm trying to remember from the last time. One of you is a student at Florida International University. Is that right?
Yes, I'm Florida International University, and you know we have the facility of wall of
right.
there. Yeah.
That's what I was about. I was going to try and connect those dots, right? We're in Gainesville at the University of Florida, but Florida International is also a NHERI network contributor, and it's also wind hazard. And they do a whole bunch of other really cool wind stuff that complements what we do, or vice versa. So hopefully you have or will have someone from FIU coming on to give a talk too, because what they're doing is really impressive also.
Thank you. Thank you so much. Appreciate it.
Yeah, I guess I have a question, like following up on that. I know that last week in the wind engineering breakout group, you had mentioned that you were working on connecting the 2 universities. And I'm wondering how research such as this would link into the wall of wind, or like if at all, or is it just like, how are you planning on connecting those 2 universities? And yeah, like what we learned here today, how can we, because I'm not in wind, right? So like, how can I connect that to there?
So one thing we can do is, it's always worth considering that if we discover something interesting, is that something that's interesting because of the nature of our facility, or did we discover something fundamental? So at FIU, they can do small scale wind tunnel experiments also. And they have also some ability to change their roughness elements rapidly, not quite to the degree of as many degrees of freedom, but they can also do something similar, but not as many degrees of freedom. So it would be really interesting if we got some outside user to say, based on what we found at UF, let's see if it actually is universally true, and go to FIU and try to do that same thing, right? That's one thing. We also just recently got notification of funding. There is a faculty member at Illinois, University of Illinois, who is, as far as we know, the very first faculty member that's gotten an NSF grant funded that utilizes both UF and FIU's facilities as a component of his larger research plan. So we're pretty excited about that. We've been, ourselves and FIU have been talking for a while about getting someone to champion that. And we finally found someone foolish enough to give it a try, and he's getting some funding. So hopefully that's enough of an answer for you, but maybe the big takeaway is just because we discover it doesn't make it true. You have to do some confirmation.
All right, why don't we break out into our breakout rooms? And if you guys know the drill, click on the join a breakout room, choose your breakout room. And thank you again to Dr. Gurley for working with us on explaining the difference between those second, third, and fourth moments and how they are either unanimous or not in different wind facilities. Those interested should join him in the wind tunnel, and everyone else choose your rooms.
Yeah, I will be I'll be in the wind for maybe 5 minutes, then I get to meet with my own students.
Thank you.